Cool. We'll just give it another 30 seconds. All right. Cool.
Yeah.
So hello everyone. My name is Anish. This is Praveen. We are going to talk to you all today about the stuff that we don't really go super in depth in with these workshops. And the reason is, there's a lot of things that we feel like certain classes at Berkeley do a really good job, and we would kind of do it. We wouldn't like we feel like kind of cramming all that knowledge into these kind of workshops isn't really a good use of your time, and rather give you sort of a high level overview of those things, and then have those other classes really hone in super deep on those certain concepts. So the purpose of this really is just to give like a high level overview of these certain things, just to show that they exist, and then kind of point you in the right directions in terms of classes, or just give you more resources as to how to really get to learn that at a much better level. Um, so yeah, so there's a certain thing called classical machine learning, which is quite different than the kind of machine learning you might hear about today with deep neural networks and all those things. And I think in the previous workshops, you all may have seen a certain subset of these. I know PCA and TSNE you all definitely saw. Feature engineering you all definitely saw. I'm not sure about SVMs. If not, we'll definitely give some. Or I don't know if we're actually giving a high level. Have you all talked about SVMs yet? And any of the other ones?
No, I don't think so.
No. Okay. Um, Again, one of the reasons why we don't want to get super deep into the concept is because we feel like the other classes at Berkeley really hone down on that, and we feel like that would be a better introduction to those concepts rather than us kind of I'm starting from scratch from there. So yeah, again, these are a lot of different components of classical machine learning, things that have existed for quite some time, that are somewhat decoupled from the kind of new things that are happening with neural networks and deep learning and all. Um, and so what actually was, oh yeah, this is the reason why we don't teach this stuff, as I was saying earlier, is that we really want to. There's a lot of things that the classes at Berkeley don't teach, right? Which is all the stuff I was talking about earlier, like how to use PyTorch, how to get your neural network running in TensorFlow, or whatever it is that there's only a very few subset of classes that are somewhat inaccessible. Some grad classes will teach you that kind of stuff, but really, like, we don't want to kind of utilize all your time teaching things that come from CS70, CS180, EU126, all of those things, right? We would rather spend this time teaching you other things that are a little bit more practical that we feel like you will not be able to get really anywhere else other than the club.
Yeah.
So that's kind of the
like maybe 182, but I haven't taken it, so I'm not 100% sure.
Yeah, I think 182 is one of those things as well. Cool. Okay, yeah, so again, just is all just like kind of building up the reasoning behind why we want to deliver this. But really, like, it just goes to show that just even in previous projects, this was a central theme. Like, I know the project that I was PL for last semester, and a project I was part of the semester before that, it was very centered around how can we achieve very similar results with much simpler models. Um, and it's a really important thing, because I know, as I had mentioned to you all a little bit earlier in the previous workshop, um, it's almost always in your best interest to start with a simpler model using classical machine learning and things like that. Um, and so, like, it's just good to kind of have it in the back of your head that you really understand why you're making that leap of faith to using these kind of more complicated models. So again, we're just trying to give a general overview as to how these classical ML concepts exist in the real world, and how, you know, we can all understand and check our intuition as to when it would work, when it wouldn't work, and things like that.
Just to jump into the project here, Ballin, Anish, I don't know if you were on the project. I wasn't, but what I read about it from the Medium and what I heard about it back when people were working on it was that they basically were trying to predict basketball playoffs, and they were using both neural networks was one of the approaches they tried, but also random forests and also just, you know, a logistic regression. So they basically used sort of a gamut of both classical and deep learning techniques.
Right. Cool. Okay, so we're just going to jump straight in, and again, the next few slides will just be kind of going over those first few bullet points on various classical machine learning concepts. The first thing is called a decision tree. And just before we even get into the bullet point, think of decision trees as a way of like kind of splitting like partitions of your understanding of the data, such that you can kind of leverage some sort of ability to classify or regress. So like more like, for example, you know, if you are trying to decide something about the weather today, there's a certain number of questions you could say, or a certain number of things you could ask, such that you can kind of arrive at some specific conclusion. So it's kind of figuring out what ways can I ask certain questions such that I can always result in an output or a conclusion that I feel most confident is true. And so again, it's like when it says decision tree, it's like I need to make decisions at all these points that will lead me to some sort of conclusion. So that's like kind of the qualitative understanding of it. To get a little bit more into the details, you kind of take your feature. You have all your features, right? All the data feature, the data, and each of the features for each data point. And it's really now replace question that I had said earlier with a simple threshold on that feature for numerical data, or categorical, depending on what you're given. But there's a simple way, just a threshold, right? For categorical, it's like, is it this specific category? Is it this specific category? Whatever. For numerical, it's, is it greater than this value, or less than, which is inherently implied. And so you essentially, the decision trees try to find what those threshold values for each feature, as well as for those categorical variables. And it tries to find what is those optimal set of kind of questions or decisions that I can kind of get the answer to, that will yield kind of the ability to categorize. So for example, in this specific tree, if you want to find out what animal you're given a bunch of features, you can ask these specific questions, right? Does it have feathers? If that's false, does it have fins? And then you can kind of just make this tree that ultimately conclude to certain buckets on the lowest level. And so again, it doesn't have to be limited to categorical. It can also be numerical, in that instead of have feathers, you can say, are there more than, or is the number of feathers more than 10? Or is it less than 10, right? And then you can still kind of branch off in that sense, and then still have kind of reach similar conclusions near the end. Are there any questions on this?
On a high level, is this kind of like logistic regression, but layered on top of each other?
You could somewhat think of it like that, but it's a little bit simpler in that, you know, logistic regression still tries to find a bunch of parameters for logistic regression, and you still try to like squeeze certain things to 0, certain things to 1, and you're absolutely right about that. But this is a little bit more simpler in that in each step, logistic regression really is like classification, and in the same sense, this is also classification, in that we're trying to figure out if it's a hawk, penguin, dolphin, or bear. But I think the means by which you reach that end is a little different, in that it's a simple partitioning of a single feature. Whereas logistic regression kind of takes all of the features, some linear combination of the features, and then tries to make that function kind of squeeze things to 0 or 1, right? So I wouldn't necessarily say it's extremely similar to that, but you have the right idea in that they're both inherently classification problems.
So how does this model learn?
Yeah, so you'll see here it says it minimizes entropy. And so there's a way, Praveen, are you super familiar with the mathematical
Yeah,
element?
so I can sort of give a high level overview as well as I remember it. Basically, the idea is like you're basically splitting. So let's say that you split on, say, if it has like, if number of feathers is more than 10 or less than 10, right? Or you say we want to split on feathers, you got to choose a number to split on. What's going to happen is you're going to divide your training set then into two buckets, right? There's the group that had less than 10 feathers and more than 10 feathers. And let's say for simplicity, we have only two classes. We have like bird and like bear or something like that, right? And so what's going to happen is the way you judge is you say, okay, let's look at these two different buckets, right? And see within each bucket, like how the more skewed our distribution is toward one class, the better, right? Because if we're able to split that one class is all birds, one class is all bears or whatever, right? We get perfect classification, right? In that basically now we say, okay, we're in the second bucket. We always predict this one class. And so there's basically like mathematical measures you can do where it's like, okay, for a given data set, with these many samples of class A, these many samples of class B, there's a function that basically says like, okay, what's the sort of, I guess like quality of that distribution? And there's like different measures. There's like entropy is one measure. So you can take the entropy of that distribution. There's also this thing called Gini impurity, which I believe I'm going to look up that, but I believe it's something along the lines of like, if you just guessed, according to the distribution, if you're like 75% one class, 25% another class, and you literally just guessed for every sample, okay, 70% of the time I'll guess is this class, 20% I'll guess the other class. How accurate would you be? And so these are some measures. And you basically just say, okay, we're going to choose the feature, choose the value for that feature so that basically on average between the two groups that we create by splitting, we sort of maximize how easy it is by these mathematical measures to select the correct class in those.
Right. So like, for example, exactly as Praveen was saying, let's say you were to say, are the number of feathers greater than 5, right? You would notice that once you split all the things that all the animals that have greater than 5 feathers and all the ones that have less than 5 feathers, it might be the case, according to those mathematical measures that Praveen was talking about, that it's still somewhat difficult to entirely classify those buckets independently. So you might move that value from 5 to 10, and then you notice, oh wow, suddenly the measure is better than when it was 5. And again, this measure is entropy, which is another way to kind of understand the uncertainty of classifying within each bucket. So it's kind of like moving that threshold value in a specific way, such that those resulting two buckets, you kind of minimize entropy or maximize your ability to be certain about something, or like more certain about it. Does that sort of make sense?
Yeah, that makes sense.
Okay, cool. Any more questions before I move on? Sweet. Okay. Oh yeah, so we were just talking about this. I think it's important to realize that it's all, whenever you threshold, it's always on one specific feature. So it'll always be on the feature of having feathers or whatever the data that you're given in whatever form. You'll always be splitting on one specific feature. And so yeah, and then and it's a tree because in the resulting two sets that you make, you just recursively apply the same logic on those two sets, and then you inherently get a tree. Okay, cool. Let's yeah, Praveen, you want to take this one?
Yes, this is just a slide from a talk about Slack's machine learning system that they use for like search recommendations and stuff like that. And I just wanted to point out what's really cool is that here they talk about using XGBoost, which is a library for training basically decision trees and random forests, which we'll talk about later, which are basically just ensembles of many decision trees. And it's just cool to see an example where like this stuff is being used in the real world. I don't know if this is like how much they rely on this versus like deep neural networks for their search recommendations, but it's at least cool that this is one of the things they use for search recommendations. Because I was just sort of, I was like, okay, we're talking about this presentation, like why this is all important. Like, is it actually important? And it was cool to find some examples of tech companies in the wild that admit to using decision trees for their classification problems. Yeah. And if we go to the next slide, we'll see another example of that, which is with Stripe. So Stripe actually has said that they have, tried, they've tried all sorts of stuff. They've tried classical, they've tried deep learning, and they prefer random forest, supposedly. I don't know if this is like super like accurate or up to date, but at least taking them at their word of what they've said publicly, apparently for this kind of stuff that Stripe does, which is like payment processing and fraud detection and stuff, random forests do work. So
Yeah. It's actually like there's like one line in particular here that's pretty intriguing to me. It's like right after the second bold. However, for most industrial machine learning applications, traditional models do just fine. And I think that do just fine is like the most important part of it because, I think I also mentioned this last workshop, but you can throw in the real world, like Google will just throw more TPUs and will throw more GPUs and will throw more layers in their network. And that's fine for, publishing these awesome articles about all these great things that they've done. But when it comes time to like actually having to do something in the wild, like it's not always the case that you have the luxury of just throwing more TPUs, GPUs, layers, or whatever, right? That's not always the answer to certain things. And so I think that's why it's important to realize that sometimes when you do end up when you do end up choosing like very deep models, it's very easy to kind of get caught in that mindset of let me just throw more layers, let me to make it more powerful, or let me just throw more compute power at it. Whereas a lot of those same problems, these traditional classical ML models will do probably not nearly as similar to those other models, but they'll do fine and they'll get the job done. And I think it's just like that kind of reconciling the fact that there exists these an extreme version of deep learning with all these other resources that are required, whereas you can also just do very similar things with much less complicated, much simpler ones, much simpler models at least. So it's good it's good to have in the back of your head. Okay. Cool. So this kind of naturally leads us into something called ensemble methods. And this is like one of my favorite things because it seems like there's a lot of things to learn even outside of just the purely model perspective of it. I feel like it gives you a lot of intuition and it's very naturally motivated, I feel like. So like traditionally we've always kind of been working with one model, right? We kind of train a single model, we have its parameters, and then we kind of plug in a test point and we see what it predicts, right? But the very concept of ensemble methods is really to kind of use a bunch of different small models. And this is to me kind of naturally intuitive, right? Like why is it that I need to believe that this one model that I train is going to be so good at all these different all that I expect it to be good at, right? It seems almost kind of unintuitive for you to put all your faith in one model. So this is kind of like a naturally motivated thing in that you're like, okay, well, why don't I just train a bunch of small things and then kind of take the most prominent output from it. In other words, like have them all vote, and whichever one output is kind of more prominent amongst all these smaller models, why don't I just assume that to be more likely? Because a lot of my small models are telling me that. So it's kind of like a cool like consensus voting system, if you will, as to what I personally would feel more confident if I had a bunch of small models give me a specific output than have one and be like, oh, this is for sure the right one, right? So ensemble methods are exactly that, especially bagging. So there are two different flavors of ensemble methods, and the first one we'll talk about is bagging, which is a short for bootstrap aggregating. But what that means is exactly what I was saying, right? Take some odd number of models, train all your data on these models, or Praveen, I don't know if it's all the data or the certain subsets, random subsets of the data.
for bagging,
Yeah.
I believe in at least the most powerful form. I'm not sure what the exact terms correspond to, but basically in general, right? You basically you do sample the data and you also take only certain features in the data at random, right? For the model. So like a given tree will see like, maybe we'll see only half the data and it might see some of the points twice. And it might only see certain features and not have other features
Right.
available to it.
So yeah, so in order to train these models, there needs to be some level of flavor in terms of randomly drawing specific training samples so that they all don't kind of become the same model. But in doing that, you kind of have these, if you have these odd number of models, you train them, and then with equal weight, you kind of, so if 5 of my models tell me that this is a dog and 4 of them tell me it's a cat, I'd most likely say it's a dog just by virtue of voting and majority voting, right? And this still applies for regression, right? You can imagine just taking like a weighted average. In this case, it would just be equal weighting, so it'd just be the normal average. But you could totally imagine having regression in that form as well. I know there's people also. Oh yeah, Praveen, you got the chat. Okay, cool. And so that's bagging, right? That seems like a very natural extension of just having one model. You kind of leverage the fact that you might have a lot of weak models and then see how you can, in aggregate, kind of understand all that. Now boosting is a little different, but boosting also is kind of naturally motivated as well. So the way boosting works is also we're still leveraging a bunch of smaller models, but in this case we're kind of being we have a little bit more intention behind it. So you train one small model, and during training time you actually try to figure out what kind of subset of your data are you really doing bad on with these models. So let's say I train this one model and I know that there's a specific subset of my data that this model just really sucks at understanding. So what you do is when you enter that second model in, it's you kind of cascade, like you kind of assign the responsibility of the second one to kind of understand that misclassified subset of that data. So like it's almost as if as you keep on adding more models to the chain, each additional model tries to understand what the previous model could not understand. And so like you try to like incrementally try to get a better understanding of all of the data by kind of allowing this new model to kind of give more weight or have more weight on those specific subsets of data that are not easily expressible by the previous models. So again, that's just like a different framework by which we can use ensemble methods, and it's just a way that it's just another way to attempt to kind of understand your data and fully explain it. And so and then going into random forests. Random forests are essentially exactly these things. Random forests are just a generic term that you can use. You can use boosting in random forests. You can use bagging. Random forest it's just a funny way of saying many decision trees. So when there's many trees, there's a forest. And so when you have many decision trees, in the same way that we have all these different small models. And again, when I say model in the other sense, those models can either be trees or they can be something completely different. So for bagging and boosting, you can actually have bagging and boosting with things that aren't trees. But random forests are specifically ensemble methods with decision trees. And so that's just something to keep in mind. And again, as Praveen was saying, the Slack actually used random forests as a way of doing some machine learning on their search system. So it's a very powerful thing to use specifically decision trees in this ensemble framework. And this is like a pretty important concept. So please ask questions if you do. And Praveen, if I miss anything, please feel free to also add.
I remember when the professor Jonathan Schuchuk, basically when he teaches 189, he mentions this quote from, I believe, Leo Bremen, who like invented, I want to say he invented bagging and boosting, or at least bagging. Anyway, he basically said that like random forests with Ada boost are like just like the best like off the shelf classifier you can get. So basically just like if you just have like a classification problem and you just want like something good to get started, you can just get Ada boosted random forests, just try them on your data and get reasonably good results. So it's kind of cool.
It's honestly like this is one of the things that kind of blew my mind, because like you're almost leveraging consensus as a means of understanding, which is like very similar to how like humans and voting systems work in the political arena as well, right? So it's cool to draw kind of weird parallels between, you know, being able to really predict something and things in the real world like political voting systems and whatnot. Anyway, that was just like a small side. But yeah, again, this is like a very powerful thing, and as Praveen said, like it's very powerful, especially in the wild. Okay, I think this was also just kind of going a little bit more in detail, but also just a still high level overview of the different components of ensemble learning.
Yeah, just speaking of wisdom of the crowds, there's the classic story where they basically did a study where they asked a bunch of people to guess the weight of a cow. And you can see the distribution here. It's like, you know, people are like an ensemble, I guess. And, you know, the average guess is like pretty close. They guessed 1,250-ish and the actual weight was 1,350-ish. So
yeah, it's like, it reminds me of that one story about how they crowdsourced a game against a grandmaster in chess. So there was like this one event where it's like a grandmaster in chess, obviously extremely good at chess, and then it was just that person versus like a crowd of like, I don't even know how many people, 5,000, 6,000 people, and like obviously the grandmaster is like really good, and he's probably better than everyone individually, but as a whole, the crowdsourced people were able to beat the grandmaster because there's so many varying opinions on what the next move would be, that they actually had the time to discuss and like play out things as a whole um, than they would have been able to individually. And I think this thing on the left that Praveen's showing is also a great example of that, right? Like when you kind of take everyone's perspective into account, you're more likely to get something more optimal towards than you would be if everyone individually was doing something. So I think, again, I think it's a really powerful thing, and I think it's really cool how it applies in the real world as well. Cool. So I think, yeah, so Praveen actually showed us I gave you oops, let me go back. The link to the slides. If you wanted,
this is a little sus because this is from like 2014, and
but I think it's still cool. I think it's still cool. At a high level, if you have time, definitely like skim through or read the paper, or at least just skim through the results. But it essentially shows that right here, if you look in bold, on this is the IRIS data set. Do you remember, Praveen?
Yeah, so I believe UCI had a bunch of data sets. They say there's 121, and I believe IRIS is one of them.
Okay, sure. Oh yeah, 121 data sets. So there was 121 data. If you aren't all familiar, UCI has a pretty awesome data repository for a bunch of ML stuff. So you should check it out online if you ever want to just play around with things. But it seems to indicate that, you know, that random forests actually perform the best as classifiers, even more so than any of those other initial models that we talked about with SVMs or anything crazy. And it's kind of cool because now it almost seems like the go-to for classifying that isn't that in the classical ML sense should kind of default be a random forest just by empirical evidence. It seems like it just seems to really capture all of the constraints of, like, you know, having not having a lot of bias in your models and not having a lot of variance in your models. It really seems to kind of account for all those things when you leverage a lot of weak learners in tandem. So again, this is just just empirical evidence on certain papers that kind of show that random forests have empirically shown to do a bit better than other models. And as Praveen said, it's from 2014, but I still think it still holds. And again, there are also are still a lot of advances in neural networks, but I think it's good to kind of remember the roots as to how everything really started. Because as we mentioned earlier, like in the wild, it's not always tractable to be using really deep models to be doing these kind of tasks when they could be doing somewhat nearly the same with these classical techniques. All right, Praveen, I think this is all you.
All right, so yeah, so we've been through decision trees and random forests. So basically the sort of some of the best of classical ML, and now we're going to talk about some more techniques for classification, for clustering, and for various sort of stuff. So the first thing is k-nearest neighbors. K-nearest neighbors is basically just it's a classification algorithm where you just look at the nearby points. If you have some, like say feature vectors, you have some distance function, and you look at all the nearby points and say, okay, the majority of the nearby points are blue, so I'll classify this sample as blue in this case. K-nearest neighbors, it has some nice properties. I want to say that K-nearest neighbors it's robust to outliers, right?
Yeah.
Yeah. It's kind of what happens with K-nearest neighbors. You can get some weird like shapes where like it can be kind of erratic in that like points kind of nearby can be like basically like if you look at like the boundary separating points of different classes, it can get really irregular, right? Because like you have like pockets where it will be one class, but the nice thing is it's kind of you have some outlier, some point that's way out there, because it's majority vote, it will still get sort of ignored. And if we go to the next slide, actually K-nearest neighbors is basically, so Spotify basically wrote this library called Annoy. I don't know why you would call library Annoy, but they did. Kind of annoying, but you know. So basically, it's this like high performance library for approximate nearest neighbors. And they claim that, at least as of 2016, Spotify claimed that it was used for music recommendation. So they would go create these albums. This is a technique called matrix factorization that's really useful in recommendations, where they said, okay, we'll represent like a user as a vector. We'll represent every single song as a vector, or I guess album, I don't know what they were doing. And they say, okay, we can basically find like, you know, maybe I'm not sure exactly how they did it, but you have like, maybe if you dot the user with the item and you say, oh, it's like highly correlated. So this user probably likes this item, something like that. And so basically they say, okay, we want to find, so they basically run approximate nearest neighbors on this. I'm not sure exactly how, but this is at least one cool use case of K-nearest neighbors showing up in the wild. Sorry, I don't know exactly how they connect from getting these vectors to running nearest neighbors on them. That's something I probably should have looked into a little more. But anyway, let's go on to linear regression. So linear regression, the case where we have, you know, nonlinear data, we do feature engineering. This has probably been discussed in a previous workshop, or if not, we'll have a whole dedicated workshop on feature engineering. That data pipelining already happened, right?
Yeah, I think they've went through all this stuff, but it's good to just remind of all the how this falls in the classical ML bucket.
And then so with time series data, so there's this technique called ARIMA. So Joey Kraut is sort of the expert in Launchpad on ARIMA. So I just asked him recently what sort of his opinion is, and he said one of the main advantages of ARIMA is that so not only here we said it can be really great just performance-wise, but it's also very interpretable. So this is again like if you have like a black box machine learning model, you don't really know what's going on with ARIMA. You can predict these time series data, but this is not ARIMA. This is just a picture of time series data. But you can predict, you know, something like a weather pattern or stock pattern or something. I mean, you know, and you can get a more interpretable result, and that's really nice. Just as an aside here, there's this board game called ARIMA with 2 A's. It was designed to be basically a board game playable on a chessboard, but that was meant to be really hard for AIs to learn. So they had this competition, like if you could train AI to beat the best humans in the world, you'd get some cash prize, and the AI won. So sad.
Classic these days, I guess.
Yep. I don't even know. I suspect they might not even have needed deep learning. They might have just like used the same chess AI techniques and just
Yeah.
Anyway, that's totally irrelevant. But if we can go to the next slide. By the way, does anyone have any questions so far? We covered like 2 or 3 topics just really quickly. So
Yeah, I kind of don't really understand what ARIMA does on a high level.
yeah, this is a good question. Let me
like,
pull up a
yeah,
page.
you can share the screen also if you would like, but it's from what I remember, so it's called autoregressive integrated moving average, I think. And so autoregressive is like another way of saying you kind of look in the past. And moving average is you know, given a certain sliding window, you just take the average in that specific window. So from what I remember, it's like essentially a parameterized way of like taking the last, you know, p time steps and then using that as a way of predicting the next time step, right, Praveen?
Yeah. So yeah. At that level, yeah, absolutely. Like it's a mathematical model where you take in basically you have some plot of like data versus value versus time, right? So if you have weather, you have maybe like rain, like or temperature versus hour, right? And you pass in some amount of prior hours, prior temperatures, and it fits a mathematical model. And I guess the nice thing about ARIMA is that the mathematical model itself is very interpretable and not like sort of a chaotic like machine learning model. And this model will predict basically, okay, I predict the next temperature for the next hour to be this, right? And then you get the temperature for the next hour, you feed it back in, you update your predictions for the hour after that.
Right. And I think they do it as like a linear combination of like Gaussians or something.
Yeah, the level below that of how they're actually fitting this model is a level that I have zero understanding of. Sadly.
But the point is like, you know, traditional autoregressive models now are like recurrent neural networks and deep learning and stuff, but it turns out that like even with just simple signal processing and statistical methods, like you can get something very, very robust still. So you know, whenever you think of something that's like, oh, this depends on previous values, it's not always the case that you should jump straight into like recurrent neural networks. You can always kind of try to see if these more interpretable models don't work nearly as well. And only after having kind of justified with that conclusion that it doesn't work as well, then should you only go into the deep learning setting.
Yeah, and this is one of the cases where depending on how much you want interpretability, you might be okay with having slightly worse accuracy, right? Depending on your problem.
Right.
All right, so if we go to the next slide. So basically like what's the takeaway? Well, we all know that deep learning is better than classical machine learning, right? Because that's why we teach deep learning. You know, for some problems, it gives the best results. You know, when your data gets bigger, when your feature spaces get bigger, it can scale because it can, to some extent, create its own features, right? So you still need feature engineering sometimes, but sometimes you can get away with having a lot of features be created by the deep learning. And, you know, deep learning is, you can do transfer learning, you can adapt, you know, ImageNet trained classifiers to many different domains. It's just really powerful. You know, deep learning is the best. If we go to the next slide, well, obviously classical machine learning is way better than deep learning, right? I mean, when you have small data, you have less data, you can get a model that doesn't overfit or behave as chaotically. You don't need to have like so many GPUs. It's more financially and computationally practical. You can interpret your model a lot easier. By choosing the model you use, you can say, okay, I want to view the problem in this way, and you can have some influence over the sort of possibilities of what your solution is doing. You can have more control over basically what sort of, you know, like types of classifications it produces. You can engineer your features. You can get good results that you can rely on and you can understand, right? So I mean, what's the takeaway? The takeaway is that it really depends on the problem, right? And like in the real world, right, these companies, like I'm sure Slack has tried both. Stripe, they said, you know, we tried both, right? They tried random forest, they liked it. They tried deep neural networks. I don't know if they liked it or not. They didn't release that information, or at least I didn't see it on their public website. I'm sure the Stripe ML researchers have opinions on this stuff, but yeah, so point being, like, you know, deep learning, like for some problems, it's just the best, right? For a lot of image related stuff, it's just the best. And you know, we focus on deep learning in this club, but that's why we have so many workshops on deep learning. And this one workshop is here just to remind that, you know, this classical stuff exists, sklearn exists, and sometimes it's the best approach to use. Really depends on your problem.
Yeah.
Yeah,
and actually, just to elaborate on that, like I think the second point is so important because, you know, as mentioned earlier, it's great to see all these like AIs that are beating specific games and all these AIs doing amazing things, and like Google has all of those TPUs and GPUs that are all set up and all these extremely deep you know, networks that are doing these things. But the perfect example, I think, is from last semester. The current president, Abiy, was doing a project called Backyard IoT, and the premise of that was, how can we do some, you know, image stuff, you know, that's traditionally done with CNNs and stuff, convolutional neural networks. How can we do that on a Raspberry Pi? And if any of you aren't familiar with a Raspberry Pi, it's like it has a very, very small compute power. It's like a small Arduino equivalent. And so can you imagine, right, trying to do all these crazy, you know, neural network stuff on something that has very, very, very little compute power? And so the problem inherently wasn't the fact that the problem itself was hard. Like if you were to kind of take that problem and just put it on a normal MacBook, you would be able to solve that instantly, right? Because your MacBook has so much more compute power. But the fact that, given the constraints of the hardware, given the fact that we're trying to do this task on a little Raspberry Pi, that we're trying to kind of put out in the wild and actually have it apply to like an actual scene that's occurring in the moment, you have to account for so much more, and you have to take that constraint into account. And so again, it's not, I really think when people kind of dismiss this, oh, financially and computationally cheap bullet point, because they're like, look, there's almost nothing my MacBook can't do, and now that I have the AWS, everything's great, and that's true to some extent. But I do feel like you also have to realize that sometimes when you actually want to apply this stuff, especially in this hardware setting like the Raspberry Pi, or if you want to build like a device or whatever it is, there is a lot of actual constraints that you just have no control over, that no matter how much money that you throw at it, really just won't really be able to adapt as well. So I think the second point is just something that you shouldn't always inherently dismiss, even though AWS and all those things do exist. And again, as Praveen said, it does depend on the problem, but it is that was just an example of a problem in which that kind of stuff wouldn't work.
Yeah, absolutely. Like, the amount of work that's being done to make like neural network accelerators, and like every year Apple's like, our chip is faster at machine learning, but the reality is that if your model can't run at 60 FPS on an iPhone, depending on your use case, it could be a problem. And that's huge. And like, decision tree random forest is oftentimes going to be so much easier to just run it without, good accelerators and all that stuff, or with limited resources.
Yeah, exactly.
All right, yeah, here's a meme I found on Reddit. I did not make this meme, but it's, yeah.
Are those pancakes or is that avocado?
I believe so that's an avocado, and then I believe those are pancakes.
Oh, that's funny. Deep learning's a problem.
Yeah. All right. So, oh my God, that didn't work. That's okay. Can we reload the slide?
Reload. Let me see.
Okay, there we go. Yeah. So basically, with generative models, for what is a generative model? So it's a generative model. Actually, there's this interesting problem. It's basically like, suppose that we have some data and we want to generate new data points, right? We basically want to estimate some kind of probability distribution. So we say like, okay, so let's say that we have we have a database of, say, animals, right? So we have like the type of animal could be like, like a cat, a dog, or like a bird, right? And the parameters are like, an animal has like a weight, it has an age, and it has a location or something like that, right? And so we want to generate some new data points for, say, the cat class. What we have to do is we look at our training data, we say, okay, there's like a distribution, there's like a probability distribution over each of these factors, right? Say that maybe the cats come in a cluster of like I don't know, cats that are like, you have like what, like you have like lions, right? Cats that are like 6 feet tall and weigh like 500 pounds or whatever. And then you have like house cats that are like 2 feet tall and weigh like 50 pounds or whatever, right? And maybe we have a sort of bimodal distribution like this. And we want to generate some new cat samples, right? How do we do this, right? It's kind of a hard problem because, even if you can classify and cluster your data, that doesn't necessarily mean you can generate new samples that are convincing and realistic to what's really going on. And so in deep learning, there's a lot of techniques that, you've learned about GANs, right? GANs are one way to generate new data. You could say maybe we train a discriminator to determine whether this is a real data point for a cat, and we train a generator to generate that. There's also the variational autoencoders. I don't know if those have been covered yet, but it's basically like you basically encode and decode. So you encode the cat down to like a single vector and you decode it back to a cat. And you basically enforce a constraint that what it encodes down to is from a very specific Gaussian distribution. So you say, okay, we're going to make sure that we compress our data in such a way that it follows this distribution, and then we can just sample from that Gaussian distribution and decode it, right? So that's sort of variational autoencoders do it that way. And this is sort of all deep learning, right? But in classical, there are actually classical techniques we can use for this data generation that basically learns. So basically mixture of Gaussian says, okay, I'm going to say your data is distributed into clusters, and each cluster is from some kind of normal distribution, right? And when you're in like high dimensional space, right, the normal distribution is like a bell curve, but in like 2D space, it's sort of like a how to describe it? It's like you can sort of imagine that you have like an ellipse, right? So like in this example, they have an ellipse, and it's like at the center of the ellipse is your highest probability, and as you go outside, it just decays sort of according to the Gaussian function, right? And so it's sort of, you can imagine like a 3D Gaussian that gets stretched and rotated and shifted, right? And that's sort of the distribution. And
I'm
make
trying
sure,
to see if I can search. Yeah, I'm trying to see if I can search
yeah, if we can get like a 3D Gaussian, that would be really cool.
or like a you mean two?
Or yeah,
dimen-
2D Gaussian.
Can you see my screen, or is it just?
Yes.
Okay, cool.
Yeah,
Okay.
exactly. So this is sort of like, you can imagine that's sort of the 2D Gaussian. You can send it to 3D, and you can rotate this distribution, you can stretch it, and you can sort of learn that. And so multivariate, basically, but the thing is that we know how to sample from a Gaussian distribution, right? Because you can just generate a random number, you map it to the probability distribution, and you do a bunch of transforms, and you can get, a basically sample points in this distribution, right? And so basically with these techniques, mixture of Gaussians, Gaussian discriminant analysis, you can impose certain constraints, like say, I want all of, I'm not going to go into the differences between them because it's been a while since I learned this stuff. But main point being that we can estimate these distributions, we can predict, we can use these both for classification and for generating new data. So it's like really cool. It's just like really powerful, because you can imagine that like being able to sample new data. It's like, this is like where, and there are some domains where GANs just absolutely are way better at this, and there are some domains where you can get decent results. Maybe I'm not 100% sure how well these mixture of Gaussians and Gaussian discriminant analysis work in practice. So if you do see an example where these were used successfully in some application or solving some problem, let me know. That'd be really cool. Let us know. We can add that to the slides for future semesters. Assuming we reuse this workshop, which hopefully we will.
So actually, I think my first semester at Launchpad, which was like four semesters ago, maybe, I don't actually remember, we did use mixture of Gaussians, and it was like this efficient reinforcement learning framework. I don't know if you remember, Praveen, Dream RL.
Yes.
So yeah, this is a while ago, but the mixture of Gaussians was actually extremely powerful, because it actually has the ability to learn non-functions. And what a non-function is, like, how functions are defined, in that for every one specific x value, you need one specific y value. You can't have two y values for one x value. Mixture of Gaussians actually have the ability, when you learn in the learning sense, to learn, distributions that are just like wiggly, that go up, like oscillating, that go up.
Whoa.
So it's really cool. There's a lot of cool things that, I think every time you take the probability perspective of your data, as Praveen was saying, you unlock the ability to generate, which is also extremely useful. But also it kind of gives you a lot of power to do things that you can't normally do in the traditional function sense. Exactly as I was talking about. So I think understanding that there exists a probability perspective of most of the things that we do. I think that's also really important to remember, because
that's also one of the reasons that we don't emphasize this stuff, is that the probability perspective is a lot sort of reliant on, like, basically, like, once you take like CS70, it's a lot easier to sort of like take this probability perspective, right? And the probability perspective is used heavily, right, in classes like 189. And sort of basically this semester, we sort of decided that we didn't want to sort of reteach probability right from scratch, like spend too much time on that. So that's why sort of a lot of this stuff we're sort of putting in this workshop instead of dedicating a lot of time to it, because it's easier to sort of understand it once you have that sort of class background, but we don't want to require that you've taken like some class before you take this workshop or whatever. So,
right.
So because of that, like, because this is sort of a lot of probability stuff, does anyone have any questions on this part?
Cool.
All right. So next up, we'll go to clustering. So I don't know if, so by the way, have you studied PCA and TSNE so far already?
Yeah, I think my last workshop was actually exactly on PCA and TSNE. So I think maybe just high level.
Yeah, so there's very little I need to say here, other than, like, if you want to reduce the dimensionality of your data, right? You can do it with a deep neural network. You can do it with PCA and TSNE. But it's just like, this is one of those things where it's just like, it's like, I just want to visualize my data in 2 dimensions, and I want to do it quickly, right? It's just like, these are just nice for that. Like, you're not going to train a deep neural network just to visualize your data if you're just exploring your data.
Right. And it seems like we came to the conclusion last time that t-SNE is definitely for visualization, but PCA can actually be used for, PCA is also useful for visualization, but PCA can also be used as a step in your training, right? Like you could decide that I just want to cut off all these other, right? Like you can take your data and you can just be like, I only want the first 5 or 10 principal components.
Right. Right. Because those can be very, very helpful in distinguishing in like classification and stuff like that.
Right. But yeah, as you were saying, t-SNE is like, it seems like I was doing some more reading online, but it seems like t-SNE is also just straight up like, let me just visualize, because it's very difficult to actually have the t-SNE step at testing time. So it seems like it's just reasonable only for visualization.
It's also, it feels like it's kind of random in that it produces very different results. Like if you run it multiple times, sometimes, at least in my experience.
Yeah, it is a very stochastic for sure.
Yep. So I was like, what, T stochastic nearest neighbors or something like that.
Yeah, exactly. And
Okay.
it's like T stochastic neighbor embeddings or something. Yeah.
And then robotics. This slide is pretty short, but like, you know, deep reinforcement learning is great, but you can do a lot with just like control theory, right? You like, you know, a lot of like, how are like, you know, guided rockets, how do they work, right? They use like control theory, they use Kalman filter, they use, there's these two concepts. Oh God, I don't even know if I remember them. Kalman filter is one, and then hidden Markov models, right? We're not going to get into these. Like hidden Markov models are taught in 188. Kalman filters are taught in 126. But it's like, you know, these are basically just these sort of, there are these techniques for like trying to estimate, for instance, like where you are, right? You get like some sensor reading, you know there's some noisy relationship between the sensor reading of where you are and where you actually are, and you track it over time. And there's basically a lot of math, a lot of control theory has a lot of different techniques for doing like feedback. So in E16B, there's a lot of stuff where it's like you're driving your car and you want to correct for like the wheel issues and stuff to make sure you're on track, and you can use different feedback systems. And then there's this other thing called SLAM where you're like, you have a camera feed, you're trying to both figure out like where the robot is, how it's moving, but also build a map of your location, right? You can imagine this is useful for like all sorts of stuff. If you're like an office robot or something like that. But yeah, so in robotics, there's like a wide mix of stuff, right? And deep RL is definitely really cool, and it's one of the techniques, but there's a lot of other stuff that you can use to build a reliable robot. This is not my area of expertise.
No, but you're totally right. And I think the cool thing is that like control theory, stochastic systems, like signal processing, all of these things are like so intricately connected that like it almost takes 4 years worth of classes to really appreciate it all. Like if you all take, I'm sure most of you have to take 16B at some point. I don't actually know. But if not, like there are so many classes that are like hinged upon those kind of earlier classes. And you'll realize later once you take upper division classes that like machine learning, all these things like signal processing, you know, control theory, like all of these are kind of different flavors of the same thing. And so it's kind of insane. Like you can consider like neural networks as, you know, control systems that take an input to an output, but when you send like a specific like you can send like impulse responses, which is like a very common thing to do when you analyze systems. Like all those same concepts really still apply. And that stuff is all very common in control theory and all that. So it's crazy to, and which is why like we feel like we couldn't do it justice by just kind of doing a single slide or a single workshop on all this stuff, because it really takes multiple classes and multiple perspectives on the same thing to really appreciate that they're all just so intricately combined. But again, we're just wanting to give you like the high levels just so you know that kind of stuff exists, so you can go into those classes kind of having the prior that, oh, this stuff actually is all connected. So yeah, that's the intent. And yeah, I guess Praveen, you can talk.
Yeah, and then so just for some courses, I mean, sort of, if you sort of look at the track of like say probability, linear algebra building into machine learning, right? It's sort of, there's E16A, E16B, there's CS70. They sort of provide that sort of foundation, right? 70 is sort of about the probability side. 16AB with the linear algebra side as well as control theory. And then sort of from there, there's CS 189 is sort of talks about a lot more detail about like decision trees, how exactly entropy and Gini impurity work, why mathematically they're good choices for, choosing how to split our decision trees. Mathematically, like there's like homeworks where you'll talk about like, how does, creating like a bunch of decision trees in an ensemble, right? How does that affect like variance? How does that affect, the quality of your predictions? As well as going into like, linear regression, classification with nearest neighbors, SVMs, all sorts of stuff, right? So it's like a lot of classical, and 189 also covers some deep learning theory as well. There's like at least in Shuchuk's class, there's like this notebook you have to fill out where you basically implement like back propagation and some like convolutional layers in NumPy, stuff like that. So 189 classical ML. There's also 188 is sort of a more focus on like introduction to RL, introduction to robotics, and that sort of is less math intensive in terms of like the prerequisites and having sort of what's the word, less focus on like proofs and stuff versus like, there's like there's projects where you're like implementing some stuff, and then there's also like it just goes over like going through some of the algorithms and stuff like that. So whereas 189 is like, 189 is kind of notorious for they have some math homeworks that are just grueling in their own way. Anish, you're taking 189 right now, right?
Yeah, what's the high?
Yeah.
Yeah, so that's just all proof stuff. It's cool though. You definitely follow professors at this level. I feel like following professors is a good thing to do. But you really can't go wrong with majority of them.
Yeah, and then with 189 is interesting because like just sort of the Shuchuk teaches in the spring, he teaches the class in a slightly different way with more focus on like programming assignments, and I believe there's like more programming assignments in his class versus just more sort of math and theory in the fall. Anyway, there's also these classes E 126 and 127. So 126 sort of builds on the probability side from CS 70, as well as going into a bit of statistics, so a bit of like hypothesis testing and stuff, but mostly probability. And they do mention Kalman filter at the end. 127 is sort of continuing linear algebra from 16AB, as well as optimization. So they talk about there's like in 127 you'll explain like, okay, for certain functions that are like, if you can bound your function with a parabola and like you can bound it like above and below with a parabola, then gradient descent will, and you can like establish certain restrictions, gradient descent works. And you like prove this 100 times, like gradient descent works on certain functions. I don't know why, but it's just, you do it. So it's like gradient descent, Then there's 120, 123. So I haven't taken these classes. These are signal processing classes. So you go into like, I believe like Fourier transforms. And this is sort of stuff it's useful in all sorts of domains, especially like in electrical engineering, right? You're dealing with like electrical signals. And then also if you're, like audio processing can be done with this, all sorts of stuff there. I haven't taken them. I can't.
I took 120, so I can talk about it a little bit. It's pretty awesome. Praveen's right. It's a lot of Fourier stuff, but I think that what's more important is that you can realize, like, I think one of the greatest examples they gave was like a long ago, like the Hubble telescope was like really shitty when they put it out first. Like one of the mirrors or focal points is off by like nanometers or something super small. And so they're on the computer and they're like, okay, Hubble, like send us the first image, right? And the first image pops up on the screen and it's like the worst thing ever. It like looks disgusting. It's all blurry, whatever. And they're like, wow, we just sent like a $4 billion thing and we just got a really crappy result. But they were able to post-process because they by like virtue of, they just assumed the Hubble was like a system. They sent specific impulse responses. An impulse response is like sending a very high magnitude input in one specific location. Like I don't even know how to describe. Like yeah, you just send a very, very sharp input. So you can imagine when it comes to functions, a sharp input would be like a single. If you guys know what the Dirac delta function is, like a single spike that goes to infinity at one specific point. So essentially they sent a bunch of impulse responses to the Hubble telescope. They received back these certain values, and then they could use those values to reconstruct or remodify or modify that original image such that it was indeed the correct image that they were expecting. But again, they did this all with just software. Like even though the focal point was off on the Hubble, they were able to post-process this shitty image and kind of and modify it to be okay. I don't know entirely if it was impulse responses or something else, but I think I remember it not being entirely complicated. I'm pretty sure from a system point of view, I think it was just impulse responses, but I also have no idea. I don't remember too well. Anyway, I think having that approach to and viewing like deep learning models or just models in general as systems, I think that kind of was hammered down in 120 for sure. And you can finish on the last two.
Yeah. So yeah, thanks for that. 120 and then 123 I've heard is like just like a lot of projects. You do a lot of like fun projects and labs and stuff like that. And to go back to 188, basically it's like more robotics focused or RL focused. So it's sort of like you start with like A-star search, you go into like stuff like Markov chains, and you go into like policy. What's the word? Value learning and policy learning, right? Policy. Ugh, I'm forgetting the term, but you go into like basically learning on Markov chains, and you go from there into reinforcement learning, and then a little bit of like neural networks at the end. And then 229A, I have no idea about this class. Information theory sounds kind of intimidating, to be honest. And then there's also some robotic stuff. 106A is the first in the robotic sequence. There's also 128. I know very little about 128 other than that it's control theory related. Yeah, sorry, we're a little over time. My voice is also kind of giving out. So I guess we'll just go over the notebook now and then probably call it for today. By the way, does anyone have any questions now that we're at the end of the slides? All right, if not, then yeah, let's go to the notebook quickly. By the way, if you have to leave, feel free to leave. Like we're 16 minutes over.
So the notebook's also extremely short. Praveen, how long do you think it will take?
I don't know, like maybe probably half an hour at most.
You think?
Okay. Not at most, but like on average, I say probably like I don't know. I'm terrible at estimating how long. Whenever I estimate how long it will take me to do something, I'm like, oh, it'll take like an hour, and it ends up taking like 3 hours.
I think maybe why don't we just go through the notebook and fill it out, and everyone can just watch. You think that's?
I would say it's probably better to, because like, so the way I've structured the notebook is that there'll be one cell that's sort of filled in. There'll be another cell that is basically asking you to do the same thing but with a different sklearn function. I think it's worth just going through and like on your own trying to basically like just getting a little bit of practice, like just looking up the sklearn function, right? And using it. They're not too bad. They're just a little weird in how they work. And basically like I would say that like we can go through the cells that are filled in here, and then for the rest of it, basically, if you want to work on that on your own time. Oh, notebook is not shared. Let me fix that. We do not have. Change to UC Berkeley. Anyone at UC Berkeley can view. Anyone at UC Berkeley. Okay, so you should be able to view the notebook now. But yeah, so yeah, I think we just go through the slides that are the cells that are not filled in, and then leave the other cells as an exercise.
Okay, cool. Should I share my screen?
Yeah.
Okay, let me do this again. Okay, you want to go ahead and?
Yeah, so basically what we're doing here is sklearn has iris dataset, but like when I wrote this, I just like found the iris data and just loaded it from the internet. So if we go up to here, like we can see that the iris dataset is like, it's like, I want to say it's like a flower dataset, and they have like 4-dimensional data, and then they tell you whether the class is like one flower or another. I believe, I don't remember the exact details, but it's like a very small data set, right? 4-dimensional data. And so the first part is we use sklearn PCA. So you can sort of see with sklearn, you run PCA. So you first instantiate your PCA with the number of components you want. So if we want 2 components, because we're doing a 2D plot, we can basically fit it to our data, and then we can get the components. we get the components, we can project our data onto those components, get our 2D data, and we can plot it. And you see it does a pretty good job of separating the different classes, right? So that's PCA. And then the exercise you'll have is to implement TSNE, and it's pretty much the same procedure. You just like use the TSNE function. And it's a little simpler in that.
There'll be a lot of copy and paste, so you don't imagine yourself having to write a lot of new novel code. It's a lot of replacing functions as opposed to rewriting from scratch.
The one thing that will be a little bit different is that you don't project by getting the components. With TSNE, there's like some fit transform or some function like that, which basically will do the, because it's not like a linear projection, so it'll project your data into the space. So that's the first part. And then Anish, the next part is on the clustering.
Oh, sure. Yeah.
Yeah.
K-means. Okay. Yeah. So it seems like again, these are all functions that you can find given these specific links that Praveen provided. But again, I think it's worth being familiar with that kind of stuff. At least knowing how to read those documentations and just like knowing what parameters to pass and whatnot. So here, Praveen made a comment that we want 3 clusters to see how it looks. This must have been run from the time before.
I mean, it did pretty well. It was a little different from the true data we had plotted earlier, but like it's pretty close.
It's pretty close, yeah.
It's basically mostly these couple here. Let me annotate. It's like these are kind of misclassified, right? But apart from that, it did pretty well.
Yeah. It seems like the later parts are decision trees. So it looks like, oh, you were able to implement this. Oh, yeah, so random forest. Okay, remember that random forests are just, you can use the, well, actually, is there?
I believe there's a random forest classifier.
Okay, nice.
It's like the same. You can basically set parameters for the number of trees and the maximum depth of a tree.
Right.
Because basically, like, this is something that we didn't talk about, but like when you have a very like tall decision tree, is very prone to overfitting because it starts near the leaves. It starts splitting on features that are just like these like small like variations in the data set. So oftentimes what you'll do with random forests is have a lot of short trees, I believe. If I don't know if I remember from 189, like something like that is like, it can be pretty effective.
Yeah, and then again, you in both cases for k nearest neighbors classifier is what Praveen talked about, in that you just take your k neighbors and whatever the majority is amongst them, you classify yourself as that. And again, sklearn makes it extremely easy because they have all these functions that usually you can just replace in other places from previous code. So all this stuff shouldn't take super long, but definitely take a stab at it. I'm not sure when these things are supposed to end, but we'll post the solutions at some point. So you, again, feel free to leave if you feel like you want to do this on your own time, but I'm sure Praveen and I will post the solutions, and we're also free to help right now if anyone wants to take a stab at it.
I believe that usually what happens is that you have the week, right, to work on this workshop, and then you can post questions and stuff in Slack.
Okay, sure.
And then, for SVMs, the last part is that there's this.
Oh.
So SVMs, right? I use SVM classifier. There is this notebook I found online that is like really cool, and that if you're interested in learning more about SVMs, it sort of goes through like a lot of visualizations of like, because SVM basically it's like you have this boundary line between the two classes that it uses to classify, and there's like a margin between like the nearest point and stuff. So there's like all sorts of stuff in it. This sort of visualizes all that stuff here.
Cool.
Yeah.
Yeah, so again, feel free to ask any questions in Slack, but yeah, Praveen and I will post, I guess, the solutions to this by the end or before the next workshop. But if there's any more,
if we forget, just remind us.
Yeah. But yeah, again, feel free to post any questions in Slack or ask any questions now. But other than that, you are all free to go.
And yeah, let's stop the recording.